When the announcement emerged from Beijing, it immediately distinguished itself from the usual scientific dispatches. China's latest report on the interstellar object, known as Threeey Atlas, was lean, technical, and remarkably direct in its conclusions. It did not offer groundbreaking detections, nor did it claim new revelations about the object's nature. Instead, it reinforced and verified a collection of observations already gathered by astronomers across the globe. The document stated with unusually high confidence that Threeey Atlas was indeed an interstellar body, following a hyperbolic, unbound trajectory, and composed primarily of carbon dioxide ice rather than water. Yet it was the report's translated summary, a single understated phrase, that captured the attention of the international scientific community. Nothing about the object has changed, and yet everything has. For a research statement of this kind, the tone was strikingly reflective. It implied that while the fundamental measurements of the object had remained consistent, the implications of those measurements had deepened significantly. Months earlier, astronomers had noticed a strange traveler entering the solar system, a faint but fast-moving speck that refused to behave like anything native to our planetary neighborhood. First, it was a curiosity. Then, gradually, it became an obsession. By the time China's data reached the international stage, Threeey Atlas had evolved into something larger than a passing cosmic visitor. It had become a mirror, revealing not only the limits of human instrumentation, but the shifting balance of scientific power in a world where the skies were no longer monitored by a single network of dominant institutions. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, first detected the object from its Chilean telescope array. Initial analysts treated the dim, moving point of light as yet another comet. But almost immediately, its orbital path refused to fit the standard models. Within days, refined calculations demonstrated that the object was not gravitationally bound to the Sun at all. It was following a hyperbolic escape trajectory, meaning it had come from outside the solar system, would pass through only once, and then disappear forever into interstellar space. The object was formally designated Threeey Atlas, making it only the third confirmed interstellar object ever observed, following the enigmatic Oumuamua in 2017 and Borisov in 2019. Like its predecessors, Threeey Atlas arrived without warning, racing across the solar system at astonishing speeds. To astronomers, such bodies are priceless. They are frozen emissaries from distant systems, messengers bearing chemical signatures from stars we may never see up close. But unlike the earlier visitors, this one appeared at a moment when Earth's scientific infrastructure was particularly vulnerable. As the object approached, observatories across both hemispheres tracked it diligently. Hubble captured optical images. The James Webb Space Telescope analyzed its infrared emissions. Ground-based instruments in Hawaii, Spain, and South America monitored its brightness as it arced across the sky. Early velocity estimates placed its speed at more than 209,000 kilometers per hour, sending it hurtling on a steep descent toward the inner solar system. But within a few weeks, something unusual began to emerge in the data. Typical comets brighten as they approach the sun because water-ice sublimates, turning directly into vapor. Threeey Atlas did not follow this pattern. Its coma, the diffused halo surrounding its nucleus, contained almost no water vapor. Instead, it glowed faintly with carbon dioxide, suggesting it formed in a far colder, more distant region of space than the comets of our own solar system. Astronomers were still grappling with this unusual chemistry when the worst possible timing struck. In late September, for a span of 36 hours, nearly every major Western observatory went offline for scheduled maintenance, recalibration, or unavoidable instrument transitions. Hubble paused for a gyroscopic realignment. JWST shifted between scientific instruments, requiring more than a full day of thermal stabilization. The Very Large Telescope in Chile entered planned upkeep. Gemini North and Gemini South both shifted to pre-approved planetary studies. None of these pauses was suspicious on its own. Each was a routine, logical part of maintaining complex scientific equipment, but together they created a global blind spot. And this blind spot occurred precisely when Threeey Atlas crossed a region of sky dangerously close to the sun's glare, making Earth-based observations nearly impossible without specialized instruments. In those 36 hours, crucial information about the comet's outgassing, its changing brightness, and its evolving chemical behavior slipped beyond the reach of the institutions best equipped to study it. To the public, the blackout passed unnoticed. To astronomers, it was catastrophic, an irreplaceable chunk missing from the light curve of a once-in-a-lifetime object. But the sky had not gone silent everywhere. Across the Pacific, high-altitude observatories in Tibet, Qinghai, and Yunnan continued their work uninterrupted. Their schedules were completely decoupled from the Western maintenance cycles, and their remote mountain locations, with thin, dry air and frigid temperatures, provided ideal observational conditions. While the world's largest telescopes were temporarily dormant, these smaller Chinese facilities recorded the only continuous stream of data available on the interstellar visitor. Their process was meticulous. Each observatory captured exposures lasting between 30 and 120 seconds, carefully balancing the need for signal strength with the risk of motion blur from the comet's immense velocity. Every image was time-stamped with millisecond precision using GPS clocks. Each one was saved in FITS format, preserving not only the visual information but a complete suite of metadata. Precise coordinates, atmospheric conditions, filter specifications, sensor temperatures, and calibration details. The files were transmitted through fiber optic networks to centralized servers in Nanjing and Beijing, where redundant power systems ensured stability even under sub-zero conditions. Engineers nicknamed these systems servers under ice. By the time Hubble and JWST reactivated, Threeey Atlas had traveled over 1 million kilometers farther along its path. Without China's records, reacquiring the object would have required broad scanning across a wide region of uncertainty, something that could have led to permanent observational gaps. Instead, China's uninterrupted data allowed astronomers worldwide to recalibrate, resume tracking, and reconstruct a precise, continuous timeline of the comet's behavior. Over those 36 missing hours, the object had brightened by roughly a third of a magnitude, an increase small to the naked eye, but scientifically significant. Its coma stretched outward toward the sun, hinting at a pronounced jet of gas and dust erupting from its nucleus. Later studies showed that the dust particles were unusually large and rich in carbon, unlike typical solar system comet dust. Once China released the data, the implications were unavoidable. Something scientifically profound and politically symbolic had occurred. For decades, the world's most influential observatories, largely Western-funded and located in the Americas, had dominated astronomical knowledge. But during this historic interstellar event, the most valuable observations came from elsewhere. China's smaller telescopes had succeeded not because they were the most powerful, but because they were the ones still watching. But trust had to be earned. Merging Chinese datasets with Western ones required careful reconciliation across software systems, wavelength filters, photometric scales, and atmosphere corrections. Chinese researchers documented every step of their process, calibrating brightness against Landolt standard stars, cross-referencing magnitudes with the Sloan Digital Sky Survey, and confirming spectral line accuracy using thorium neon lamps. Independent teams in Hong Kong and Taiwan validated the measurements with impressive precision. Once integrated, the combined global dataset reached unprecedented accuracy, fixing the object's eccentricity at 1.19 and narrowing its positional uncertainties to within 1/5 of an arcsecond. The verdict was irrefutable. Threeey Atlas was of interstellar origin. Beyond the numerical certainties, the episode exposed uncomfortable realities about the world's astronomical infrastructure. Despite frequent rhetoric about international cooperation, observational capability remained unevenly distributed. Of the world's 30 largest telescopes, those with mirrors over 6 meters in diameter, 2/3 belonged to Western institutions. China's instruments, typically between 2 and 4 meters, were smaller individually but organized into an automated, distributed network. In situations where continuity mattered more than raw sensitivity, this approach proved unexpectedly superior. Large telescopes excel at deep imaging of extremely faint galaxies, but they cannot observe the same target continuously for days without interruption. Smaller, more flexible observatories can. For fast-moving objects like Threeey Atlas, persistent coverage was more valuable than sheer aperture size. During the blackout, China's robotic scheduling software dynamically reassigned telescope tasks as weather changed or as the comet's angle shifted. By stacking hundreds of short exposures and statistically combining them, the network achieved a signal-to-noise ratio comparable to far larger instruments. Persistence, not prestige, became the deciding factor. The implications ran deeper than the comet itself. The episode raised the question of who gets to see, and therefore define, the universe. For decades, the largest telescopes had represented not only scientific capability, but geopolitical influence. Threeey Atlas flipped that narrative. The most complete record of this rare, cosmic traveler came not from the biggest mirrors, but from the observatories that simply never stopped watching. When the final analysis was released, it confirmed everything the earlier data had suggested, that the object was composed primarily of carbon dioxide ice, that it had formed in an environment radically different from our own, and that it was now headed back into interstellar space on a one-time journey past the sun. Yet beneath those conclusions lay something more profound. The discovery marked a subtle but unmistakable shift in the architecture of global knowledge. The chain of observation had become truly international, and its strongest links were no longer where they used to be. A single 36-hour blackout had shown how fragile, centralized scientific authority could be. The universe does not care who is watching, only that someone is